Once again, I welcome Harpreet Singh Jatana sir to this session. Today, second day, and this is the first session. Today's session is the second session of Harpreet Singh Jatana sirs. So I would like to hand over this session to him so that he can deliver his talk. Thank you.
Good morning, everybody. And in this today's session, we will be talking about the physical implementation of the circuit and the packaging part. And because the chip, it's not possible to physically handle, it has to be put in a encapsulation, and what are the different types of packages available and what are the testing related issues. So those things we will discuss, and I will start with the testing and packaging part first, and then we will go for the analog layout and physical implementation of the analog design. So I will start with the packaging part, and I am just sharing the screen. I hope the screen is visible. So is it visible now, screen and my
Yes,
voice?
sir.
Yes, sir.
So should I start?
The screen again disappears, sir. Yes, it's coming.
I think it will come. Okay. So this is a basically, if you see the cross section, and this is the real picture where you can see the various metals passing through. You can see here, if we start is the top metal 5. This is metal 4. This is metal 3, and this is metal 2, and then this will be the metal 1. And these are the plugs. They connect the two metals, like this metal, which is a metal 3, and this metal which is a metal 2. So here they are connecting these. These are known as via, and these are tungsten plugs. They are known as via also. And this area is of course dielectric passivation layers. As you can see, the top metal is thick. You can see this is the thickness because it's a cross section. So you can see it's thick as you compared with this. So normally when we use an aluminium till 180, 130 nanometer for metallization, aluminium is used. It's not a pure aluminium. Basically, it's a 5 stack. It's like first is a tin, then it is a aluminium, and there is some copper, and there is some silicon atoms in this for electron to prevent electro migration. And titanium is also there first as a liner. So it's a very in this layer there are around 5 different materials which are put, and it's a stack of 5 layers. And the thickness for metal 1, metal 2, metal 3, if you are using aluminium, it is close to 7,000, 8,000 angstrom. And the top metal normally is made very thick, 20,000, 30,000 angstrom. 8,000 is the lower metals, 7,000, 8,000 angstrom, and 20,000, 30,000 angstrom. And normally for local interconnects, these lower metals are used. For local interconnects and for global, these are used for power supplies and all those things where you have to take a lot of current and you need a very, very low resistance. Because of this the thickness resistance will also be less. So this is again you can see here it's a P substrate. It's a double well process, and it's basically an epi wafer here. That you can see the epitaxial layer, and this is one well, N well. This is another well, and then in this N well we have this diffusion P plus source drain, and in this P well we have this N diffusion, and this is the gate. This is the gate for N transistor. This is the gate for P transistor. So this is the connection you are seeing here. Normally here it's basically a silicon P plus on top, and you cannot put directly aluminium here. So the some liner it has to be given here. That is salicide, cobalt salicide. So cobalt is put and it reacts with the silicon to make a cobalt salicide, and then you put on top of it aluminium like that. So this is the connection for source drain. This is the connection for source drain, polygate, and you can see this is goes up to metal 1. This is metal 1, and this is the plug, which is a via tungsten plug, metal 2, metal 3, metal 4, and like that. You can have many metals, around 12 or 13 metals in low geometry, because of to increase the component density. So now, first of all, is a testing. Testing is, as you are aware, to testability is very, very important, and you cannot have all you cannot observe all the nodes at the output pads, because output pads will be very small, very less in number, and the input nodes will be very high. So then there is a concept of observability and how you can see the nodes at an output pad. So DFT deals with all those things while designing the circuit. For a digital circuit, you have to put scannable chains and things like that. And for an analog, what you have to do is you have to bring out certain nodes which are inside the chip to outer pad, which we call it a test pad, so that you are able to probe those nodes. So that is important. And if we see in a, you can see here, because this is the complete chip here. Sorry, this somehow this is not able to work properly. So this is the complete chip. If you see here, so it will be like this. So now the pads will be put here on the peripheral. It will be there, some power pads, some IO pads, and finally here you will have some circuit. Some circuit will be there, and there will be some input pad. There will be some output signals and like that. So for example, if this is the one, so you are giving input here and you are observing output here. So these are the internal nodes, these one. So finally, for a good testability, you should be able to observe this, but it's very difficult to observe because this is not accessible. So in a digital thing, we use various techniques like DFT, so that the status, the voltage at this node, we are able to bring it at this pad, And for an analog, normally if I want to, if it's a sensitive node, so what I will do is I will connect to a test pad here like this. So then I am able to see this node, and while doing the wafer sort, and while doing the package, these test nodes, test pads, They are not packaged. It's not required because it's only you are internally probing, and there is a e-beam probing also. By e-beam also you can probe, but it's a sophisticated equipment. So automatic test equipment are there, which can connect any, uh, which can test any circuit, digital and analog. So they have various channels like 256, 500, 12 channels. So at each channel you can program input voltage, output voltage, if it's analog, if it's a digital, what is the frequency and things like that. So this is these are known as automatic test equipment, and Ultraflex is by Teradyne is one of the very famous tester which most of the semiconductor houses they are having. LTX Credence is another. Then there are certain testers which are PC based. These automatic test equipment are very expensive, 8 crore to 10, 12 crore in that range, and maintenance and all those things to operations of these are quite expensive. So there are certain PC based automatic test setup which looks like this. It comes in the range of 1 to 2 crore. And then there are some how to handle these wafer prober, how to handle the wafer, because finally the wafer will be tested. So how to handle the wafer, there are certain equipments as you are seeing here. So these are known as wafer prober. So this wafer prober will handle the wafer, 8-inch wafer, 12-inch wafer, and in a box which we call it a cassette, some 20 wafers will be put, and the cassette will be put in this prober, and it will take one wafer one by one, and that will be tested. And how the connections are made by probe cards. So this you are seeing a probe card here. You are seeing needles here. So these needles will make contact to the probes. These needles you are seeing, so they will be sitting on the probe. They will be sitting on the pad, and they will make contact there. And finally, from here, edge connector. They can cable. This is a edge connection, and from there cable will go to this tester. So all the signals from the tester will go to by this cable through this pad to this probe card. So needle, it will go here. So you can go give any stimulus and check the output. So these probe cards, these they come in two types: blade type, epoxy type. So we will not go in much details. So then RF testing, you have another RF prober stations are entirely different. You need spectrum analyzer because RF works spectrum analyzer till 50 gigahertz or more. You need impedance analyzer. So these are some of the testing equipment which are required. And for a MEMS testing, there is no automatic test equipment for each particular device. You have to jig up your own test setup. And these are some of the big pictures. Only these are taken from the net, various testers, electroglass, what type of it looks, RF wafer cover. So I will skip on this. And next comes important thing is your packaging, because this is a die, and you cannot handle the die is very small, and how to use it on a board. So there are two basically techniques. One is chip on board, that we will that slide will come later. So first is we will put in a package. So it's a basically a mechanical connection of chip to the board. And as you are seeing here, this is the chip, and these are the leads on the board. So we will put a wire here, yellow color wire. It can be aluminum wire or gold wire, silver or normally aluminum or gold. So you make a from the chip pad, you are making connection to the lead terminals, and you are you are encapsulating the whole thing. So it helps in mechanical connection. It removes heat, because whatever heat is produced through these wires, it will go to the package. Whatever heat is produced through these wires, it will go to the package, and it package can dissipate heat. And it's a mechanical strength. It is providing mechanical strength. Another thing is it's easy to handle. You cannot handle a 1 mm by 1 mm die, or it's very delicate, and it's impossible to handle. Package will be bigger, so you can handle that. But nowadays, packaging has become very, very important because, first of all, you made a very good circuit here. It's working very fine, very high speed. But these wires, they will add to parasitics, particularly inductance. So these wires will restrict the higher frequency operation. So a lot of innovative ways are there in the ways in which you are able to reduce the effect of inductance, and that we will see. And packing style is basically identified. There are different type of packages: plastic packages, ceramic packages, Cerdip packages. So mainly Cerdip are not being used. Mainly there are two which are used for package material: plastic, they are very cheap. And if I want, most of the commercial ICs which we are using, so they use plastic packages. And if I give you an idea of the cost of packaging, it is close to 80 paisa, 90 paisa per pin. So you can say it over 1 rupee per pin for mass manufacturing. So if you, there are a lot of packaging houses in Singapore and Malaysia and Kuala Lumpur and all those places. So they will quote this only some 90 paise to 1 rupee per pin. So if you have a device 200 pin, so it will cost you at least 200 rupees for a plastic package. And the flow of this plastic packaging line is different than ceramic. They are higher levelty packages. It can be used at high temperature range also. So for defense and other strategic needs, ceramic packages are used. So package style, how you mount, what is the material and what is the geometry. And mounting style is basically DIP, is dual inline package, which you have seen mostly. I will show you the pictures here, and physically I will also show you some of these. So how you are mounting. So normally on a PCB there will be holes. Package will have some leads or legs. So you will put that the package in those holes and then solder it. That is a dual inline package and PGA, pin grid array. So all these are that type. Then there are a surface mounting. Normally, if you have seen the boards which become complicated in this, there are so many interconnects on the board, like a laptop or a mobile PCB. So it's a surface mounting devices, and that is used. And there are small outline devices, basically small outline package, and QFJ and all those. They, it depends on the leads, the type of the leads. So it can be J type, J band, Z band, and all those things. So you can see here this is a dip 14 pin, because these leads are there. They will go in the holes and you will solder it. So PLCC is also one of the package. It's a leadless chip carrier, and it's a plastic. This is a ceramic. This is a plastic. This is a ceramic. It has a window also. That is, it is a lid, and it's transparent because it's an imaging device. It wants to, you want the light to fall on this particular thing. So some of these packages are ceramic packages. Basically they come in standard sizes, like you have 225, 248, 560, 387, like this 280. So this package comes and you will put a die inside it and bond it. So this is a ball grid array BGA 560 pin package. This is again a PGA package in 296. So you can see the leads here, and at this also you can see the leads. You can put it there on that, on the PCB board. And so dimensions that matter into an IC package footprint, basically, if a, just for an illustration, this a DIP package is used. So the thickness of these leads, it will matter, because finally it is causing a resistance and inductance, parasitic. And that important pitch, this is the pitch which also is important. And then you have the lead width, lead length, and total carrier length, because how much signal has to go from the chip to the outside world through these leads. So all these things, they matter in the design of a plastic package or a ceramic package. So these things are important. And then there is a, because package, it will have some thickness, as you can see, it will have some thickness, which is this dimension. So the package thickness, but like in a watch, wrist watch, so you want a very sleek thing, very thin watch. So if the package is thick, then definitely the watch also will be. And moreover, you want to reduce the cost also. The package, some cost is involved. So what is possible is you can put directly the chip on a PCB, on a board. So this is the chip here. So it has been put directly, or you can see here, this is the silicon die. So this is the PCB. So die has been put directly there by some glue. It is pasted here, and then on the PCB, you will make the pads here while designing the PCB, and finally you will bond this from here, silicon from the chip to the PCB. You will bond like this, and finally you cover it. You encapsulate by some material, which you are seeing this, so that these bonds, because these are wire, because if you keep it open, so these may break. So finally you encapsulate this. So this is normally used in calculator, watch, hearing aid. So small these kind of devices, these things are used even in mobile phones, because you want a very sleek, very thin product. So these kind of, but here the limitations is you cannot go beyond some 100 or 120 pin chip, 100 pin, 110 and 120 pin device. You cannot go beyond this. It has to be less than this. Now I will try to show you some of these physically packages if it is visible in the camera. Let me. I am switching on this camera, and first I will show you the wafer and how the device looks like. The things, you may not be able to see the chip, but are you able to see, or it's very difficult to imagine? So this is a wafer, it's an 8-inch wafer, it's 720 micron thick, and you will not be able to see the die here, and because of the resolution, because these dies are very small, some dies are 5 by 5 and some are 10 by 10. So you can see this is one of the package. If you are able to see it, so you can see these wires, there are close to around 70 to 80, 82 wires here in one side, here in one side. So these are very thin, very delicate wires. That is why this outer ring is there. So when the device is basically, it's a surface mount device. So during transportation, so this is the protective layer, and so that these leads are very fragile and very thin. So they are very close to each other, pitch is very small, and they should not touch each other once. So then you will have shorting of these pads. So during transportation, it is done like this, and when the user uses it, this outer frame is removed, and these leads, these wires, they will sit at the PCB where at each pad. So for high pin count devices, it is like this only, and then there are certain devices where there is a window, particularly imaging device, which you are seeing here. You may not be able to see the window. It's a transparent, and it's basically here leads are there. It's a pin grade array kind of thing. So these are the different type of devices. This is another device which is a BGA. It's a ball grid array, and this is another. It's a low. It's a small package. It's known as small outline package. So you can see here the pins are two sides only. Some 24 this side, 24 this side, 48. So it's a very thin package also, and very small package. So these are various types of packages which are there available, and depending on the requirement, these can be used. So I will not. So basically, the wafer is tested, and good dies are taken out, and then the wafer is diced. You have a dicing saw. Each die, then you will get individual die after dicing the wafer, and then you will put the die on a package and then bond it. So this is the equipment which is used for bonding. It's known as a die bonder. It bonds the die on a package, and then there is a wire bonder. Wire bonder means the wire it which goes from the pad of the chip to the package. So that is wire bonding. And finally, then there is big furnaces for sealing purposes, hermetically sealing purposes. So there are is multi-zone. It's basically a long furnaces, and there are 5 zones. Each zone is set at a particular temperature. So that is the packaging process basically. And there are these are the standards, military standards 883 and all those things to do the hermetically sealed uh, packages, so that no humidity or anything can go inside the package which can have a detrimental effect on the chip. So all those things are done, and again, these are some which I was showing you some of these pictures of different types of packages only, and these are the TO packages. These are basically for 8-pin TO8, TO16. So you can see here, this is a metallic for heat dissipation. These basically for a very small die like a power transistor or a single transistor which dissipates, which takes more current, dissipates more power. So these kind of TO packages are used. So each package, and this is the package for a CCD device, which is a long device, and these are custom made packages. So the making of these packages are very important. And finally, another thing which I want to emphasize is these nowadays, because of the requirement of an AI, and AI, you need a lot of for edge computing, you need a lot of memory, you need a lot of you need very high speed processors, and all those have to be packed. So the packaging is seeing a very like a drastic change in the packaging, particularly because of AI systems. So they need lot of memory. They need a lot of high speed processing, because a lot of data has to be processed at a very small time. So this is the requirement, and for a system on chip concept, circuit is big, and functionality, because it contains a lot of different kind of a function it is doing. So the packaging also becomes important, and sometimes RF signal, like a RF device is there, you may have done RF in a gallium arsenide, and logic you have done in a silicon substrate. So there are two different substrates, and you want to package. And if there is a MEMS device, which is a sensor, and then sensors will be a separate die. So there will be a 2 or 3 dies, and but you want one package in that. So that concept is of a 2D or a 3D package. So basically, you see, there are these are some of the slides of IBM. They are doing a lot of good work in 2D, 3D packaging. You see, this is the motherboard. It's a very simple example to explain. classically, this is the motherboard. I have three different chips. I have made three packages, right? So I have bonded to this. You can see I have bonded to the motherboard. This is the package and this is the chip. So these are three chips. These are discrete chip on package. This is known as discrete chip on package. Then you have heard a concept of system on chip, SoC. What I will do is whatever circuit is there in these three dies, I will make one single die. That is okay. That is good. One single die. This is the package. And so you have reduced the size, you have reduced the power, but the yield, because the die has become much bigger, you lose in the yield here. So that is okay. Then another line is system in package, SIP, system in package. So basically, what we are doing is here we are not going for an SOC. We are not going for an SOC, but as you are seeing these three chips, they are having three different packages. These three dies, they are mounted on three different packages. Here we are not doing, we are having one single package, and you can see that is also known as MCM, multi-chip modules kind of a concept. So we are putting three chips on one package. So then you will see, ask what is the difference between this and this. You see the difference is because these three chip, they will have to communicate amongst themselves. If this chip is communicating with this, how the signal is flowing? Signal is going to the package, to the board, and through the board, it goes to this. So the time taken for a signal to go from here to here, the path is long. Whereas here, in this case, why it's faster? Because within the chip only the signal is traveling. It doesn't go to the board. Within the chip, it is traveling from one part of the circuit to another part. So in that way, it's faster, it consumes low power also. So here, it doesn't go to the board, it goes to the package only because those lines are there in the package. It goes from one chip to another, though the dice are different. So what I am gaining is I am gaining in the yield also of these dice. Here the yield will be affected. So here the yield will be more, and I am getting the advantage of you can say the signal travel time and speed and things like that also I'm getting. So both these concepts, system on chip and system in package, you have to evaluate basically. So there is a concept of 2D 3D packaging, and this is a example of 2D, and people are talking about putting even stacking various chips, and I will show you some of these, but I will not go with. You can see this at the IBM site. These information is available, so you can go through this, and then we will go to the important part, which is the physical design, physical implementation. That is important. So I will start with that. So physical means how you are able to, let me do the layout, basically the layout of various components, what are the issues, and how we can do this layout, and to do a better layout, like you have to make a circuit like this. So this is what our goal is, and as we have seen yesterday in the analog flow, from specifications we make a front end architecture which will be spice list, and then we'll do the simulation. Then if this after simulations, if your specifications are meeting, then we will do the layout. So we will talking about the layout. Then what is a layout? Basically it's a process of creating geometries, mask geometries. So based on the layout, your mask set will be created, and the from circuit netlist layout information is given to the mask fab, that in a format which is known as GDSI, GDSII, or GDS file is given. Based on GDS, masks are prepared, and based on the masks, you will do the fabrication part. Just I will show you one of the masks if you are able to see here. So this is one of the mask set, you will not be able to see the finer uh, polygons in this. This is how it looks. It's a quad, and this is the in fact this is a 5x mask, and if you are able to, you won't be able to see the various. There are around close to 28 designs put in this. Some these designs are bigger, some are smaller, but may not be that visible. So it's a 5x mask, and cost of this mask sets is normally close to, it varies from 4,000 to 8,000 depending on the which mask it is. If it's a critical mask, it may go as high as 6,000, 7,000 rupees also. So these masks, they are used in the fabrication. That so we will discuss about the layout concept. So this is an first stage op amp. It will look like this after layouting, but we will see how to do this. So we have yesterday we saw those layers. That was the reason for discussing the CMOS flow, and I have shared that paper, that tutorial which contains the CMOS, because for a designer he also should know what is the fabrication flow, what is the fabrication process, because finally the design will be manufactured, it will be fabricated. So what are the issues during fabrication, he should be aware, and he should be aware of the layers. So we have seen there in a dual well process, there will be two masks for N well and P well. And these masks will, like here in the green N well mask, they where the polygon is, N well will be created. N well will be created means the implant will be done in such a manner that N plus substrate will change to N plus. So in this area on the wafer, then there is an active area mask. Active area we told where the component will be made. That is an active. And rest of the area is field where isolation will be there. So all components will be properly isolated in rest of the area. And then there is a gate mask where gate will be formed. And then there's a contact, you can see very small, there's a contact mask where contacts will be formed. And then there is a metal lines will go, metal mask where via will be formed. These are also very small. And then metal 2, metal 3, metal 4, like that. Photolithography process, you all know, I will skip. Hello? Hello? So this is a cross section of a PMOS, and you can see the layers, various layers here, and like what we discussed in a single well, this is the N well. So you have this green dashed polygon which represent N well. So when you are layouting this, so you have to select these layers. So how you will, because if you have to lay out a PMOS transistor, what you will do, you have to first do select the N well layer, green polygon. This green polygon is there. Then you have to make a substrate contact. So in a substrate contact, this is N well. So you will choose N diffusion layer also, N diffusion layer here. This is dark green, this is N diffusion layer, and you will make it active, because for making a contact you will make active, because if you don't choose a active layer, then it will be become there will be a fox there, like you are seeing a fox here, it will be, there will be a fox where you don't choose. So you choose active, and then you choose N plus, and then you choose contact. These two small, you have chosen contacts, and then you have to choose here N well, you have to choose an active layer. So this is the active layer in this one, this whole where I am moving the cursor, this one is the entire active. And because you see from here to here, from here, this point, this line is coming here, this line is coming here. Okay, so this is the active region, and other region you will have Fox. This is isolation. This is isolation. And then here it will be a poly. You have chosen a poly layer, LP. So here will be a poly, and the rest will be, this will be source drain, this will be source drain, this will be diffusion. So this we will see in a bigger. And these design rules, the semiconductor foundries, they allow designer to design only the layout pattern on top view, and thickness of the layer are fixed by the foundry. Thickness of these layers are fixed by the foundry, and the designer have to design the layout according to these rules. And the purpose of design rule is like dimensional precision, to it's a warranty of dimensional precision. And like a certain dimension only can be fabricated, and minimum and maximum both limits are there. And that is the reason. And design rules come in these minimum width rules, minimum space rules, extension and overlap rules. What is the meaning, we will explain. Like poly, if a poly line, there's a minimum width, like 100 nanometer, 90 nanometer. So minimum poly should be 90. You cannot have an 70 nanometer poly. Then there is a that's the minimum width, and there's a spacing, poly to poly. So for a 90 nanometer poly to poly spacing rule may say the poly to poly spacing may be 120 nanometer or 130 nanometer. You cannot have very close poly. The reason is while manufacturing, because then the polysilicon is deposited on the entire wafer, and during the poly mask, where poly is not required, that is etched. This area will be etched. If they are so close, etching is a chemical process. Okay, it's a reactive ion etching, and it's basically a dry etching, and it's a chemical process. And in that, it's a chemical reaction. So you will not be able to etch properly if the space is not sufficient. So that is the reason why you will have proximity effects and neighborhood effects and things like that. So there is the foundries know how much minimum area is required here, and then you have made a well here. You have seen, and this dotted line is the well, and then in a well you want to have a diffusion here. So the from the well edge to the diffusion there should be some minimum, because otherwise if this rectangle is sitting very close to this, while manufacturing it may happen that this edge crosses the well even. So in a N well, if I have a P diffusion, there will be a spacing inside and at the edges how much you have to leave. So that is very important. And then you have a metal line, you have a metal thickness, metal to metal spacing, and then you want to make a contact on the metal, and then the contact, because you this is the contact. Now this contact should be there on the middle of this. So that is how then you should have extension beyond the contact. This one which arrow is showing. So there has to be some extension beyond the contact, so that the contact resistance is minimized and contact is proper in case of via. So these are the certain rules which are important, and the foundry gives. And in a physical verification, these three things are checked. Design rules are checked. If there is a violation, tool will tell you. The caliber is the tool which uses this, and it will tell you the location where the violation is there. Electrical rule will also check. It will electrical rule means open and short. It will check for open. If there is some component is shorted, it will tell you. Layout versus schematic. Once you have done a schematic, in a schematic there are 1 lakh components. After layouting, it should be exactly 1 lakh component. There should not be any subtraction or addition of that component. So that is the equivalence checking. The number of components is same. That is only whatever schematic is there, that has been converted to a layout. So no component is missed, no component is added. So all these materials, resistor, capacitor, inductor, are used in the. So we will see the layout of these things. So analog circuits, they use a lot of resistors. So the value of resistors can change by 20 to 30%. So that is it's very important. And so you have while designing, you should know that the whatever value you are putting a resistor, it can change by this much variation. And tracking between matching of these pairs, which we will see in the further slide, that is also very important. So sometimes laser trimming is used for thin film resistors to make a very, very precise resistor. That also we will see. But here you can see here resistors, whatever we have seen, resistors can be made from well, resistors can be made from N plus or from P plus. And finally, you can see here if this is a resistance, and finally uh, depending on the W and L of the sheet resistance, and this is the contact where you will make, like if suppose if it is a well resistor, so in the well you will make two contacts, and contact normally the foundry will tell what is the resistance of a contact. Like in a 90 nanometer it may be around 3 ohm or 4 ohm. Each contact, the resistance of each contact will be 4 ohm. So 4 ohm here and 4 ohm here, 8 ohm have gone here in this. And then if you want a resistance of around say 100 ohm, so 8 ohm is gone here, and then you have to choose L and W, and depending on what the sheet resistivity is, you have to choose L and W, so that overall you get whatever value you need, whatever resistance you need. That way you can have that. So these are the cross section of the various resistors in a poly. You will have poly, and at the two end of the poly you will make contacts. So in case of a P plus diffusion, so within N-well you will have a P plus diffusion, and these contacts, uh, two contacts you will make. In case of a well resistor, you will make contact of the well, and the dimensions of the well depends on how much resistance, what is the value of resistance, resistance you need. You see, if you need a resistance which is quite high, say around 100K, so you will not use a very long, like for example, if I give a very simple example, if the resistance you need is say 100K or so, say 100K. So, and sheet resistivity RS is, say, I assume it is 2K per square. So, how many squares are needed for making 100K? So, it is 50 squares are needed. So, what I will have is a long wire, and like this. 50 means if this dimension, you can see here, if the length, if the width is, you can see here, if this dimension is 1, then the length is 50. So then only it will make a 2K by square resistivity, and so this L is 50 and W is 1. So one way is this. In a front end design, it is okay, you will make the contact. Where you will make the contact? You will make the contact at the two edges. What is this? You will make the contact here, and another is the last, you will make the contact here. But question is, this is 1, this is 50, right? In a front end this is okay, but if you, nothing wrong in it theoretically, but practically the this thing is not going to materialize, and there will be a lot of issues, and there will be a lot of resistance mismatches. And what we have to use is, we have to use, you can have 5 or you can have length of 5, we can have 10 such segments here, and connected like this, like this. So you don't use a, we have to see the your aspect ratio wise also, and we will see what is the reason when we fabricate this kind of structure, what will happen. So those things we will see. And so use of long strips, normally you will, there are two options you can have, like this, that is a serpentine structure. You are making contact here, you are making contact here. Or you can have, you see, or you can have sectioned, you are making contact here, you are making contact here also, and this is connected with a metal line, this is connected with a metal line. This is connected with the metal line. Metal resistance is very small, milliohms. Okay, so then what? Because here the reason is, if you want very, very accurate resistance, you will use this. The reason is because here you are having corners here, and it's very difficult to model the corners. Here you are not getting cornered, straight line. And these two segments are connected by a metal whose resistance is in milliohms. So, but here there are corners, and it is very difficult to model the corners of the resistance. It may not be very, very accurate resistance. So this will be very accurate. But only thing is, it will take more area, more silicon, because of the design rule of these two contact separation. Here may be less, here may be more. So slight more area may be required for this. So this is how, as I am telling, so you will have a corner here, and the current, it's very difficult to model the corner. So resistance at the corner cannot be estimated correctly. That is the reason. And current flow at the corner is not uniform, because how the current is flowing in this direction, then how at this point crowding of the current will happen. And what is the case here? Current flows here, and now here metal comes, and metal is not giving any resistance. So the crowding of the current will not happen here. It will come directly because it's a metal. And again, current moves go like this. But here it's not, it is the same resistance here. It's not a metal here. So the current flow here and here will be different. So all those things also matter in layout, small things, they matter. And okay, then you can have a shielding resistance widely used. So if you shield the resistance means, and this is a particularly, you can see here, this is the resistance S and S, and this is R. Here you are making a contact and it goes like it. Here you are making a contact. This is one, you are making a contact like this. Okay, so, and you can shield in, make this resistance in a well and connect the well to a DC potential. So that way you can use, and N-well resistors, if you want to have a large resistance, you have to use N-well resistors, and they are enclosed by a substrate for shielding. As you are seeing here, the outer ring you are seeing here, the outer thing, this is a substrate. So you are shielded this. You have made the resistor within the well, and these are so many well contact, and you have made a ring of these well contacts, and they will be connected to a DC potential, so that it becomes shielded. And these are the resistance, like this. You are seeing here, this is the resistance, this is the resistance, and this is the well. This is the well here, like this. It goes like this, it goes like this, then it goes like this, it goes like this. This is the well, this is the resistance. You see here, it goes, it is like structure like this, like this. This is one resistance, this is another resistance. So it is like this way. It is, these resistors are layouted. You see, there is a minimum dimension of this also, 3.8 or 1.8. Because if you make it very, like, if you see, the value of these two resistance will be same, because it depends on, it is 3.8, it is 4 micron and 3.8 micrometer. Here it's 1.8, it is 2 only, right? If you see, and the length is 10 micron, and this is 2 micron. Here also the length is 10 micron, and but the width is 3.8, or here, because I wanted 4, so it is 10 by 4, and this is 10, this is 4, it is 10 by 4. Here it is 10, it is 2. So, but instead of 2, if while fabricating, if it becomes 1.8, then you see the effect. It is 10 divided by 1.8, and it is 10 divided by 3.8 from 4. So what is the error? So that you can calculate if the dimension is more, because here while fabricating, this also is changing 0.2, this also is changing 0.2, but this 0.2 is changing from 1.8, and this 0.2 is changing with respect to 3.8. So error is less here. So that is the reason very small geometries, and they will also, if there is an error, the error will be bigger here. So the systematic error will be more. So that is how the foundries, they will tell that once you lay out a resistor, what is the minimum width you have to keep, or what is the minimum width. So don't go beyond this, don't go lower than this. If you are going lower than this, there will be error in that. Error will be more. So you have to keep it dimension which is more than this. Then the size of the area to be etched determines the etch rate, because finally etching in a fabrication process also is there. So you see here, if three elements, three resistors are kept like this. So you see in this region the etching will be slow because there is less area. Whereas here the etching will be more. Right. So where the etching will be more, this means this dimensions here, it can be over etching in this. Here it can be over etching. So what will be the effect? The width of C and A can be reduced because of over etching here. But at B, at both the sides, there is no over etching. The etching is less. There will be under etching. So this dimension of B will be more as compared to A and C. So you wanted ABC, all resistor to be same, but what is happening is after fabrication, front end design it is okay, but after fabrication, in simulation it will show you okay, it won't show any effect. But once you get a silicon, so the device performance will be affected because your B dimension is same what you had planned, but A dimension is reduced, C also has reduced. Okay, so then what you do? Because here we want of all these three elements, the surrounding should be same. The surrounding should be same, which is not the case with C and A. What I will put a dummy here. I will put a dummy here. I will put a dummy resistor here. Now you see that A is also seeing the same surrounding, B is also seeing the same surrounding, C is also seeing the same surrounding. So that is the surrounding effect is same for all the ABC, and then the etching at these areas will be the same. So that is how you are putting a dummy strip. They are not connected to anybody. If your resistance is a well resistor, it's a dummy well you are creating here and here, and normally you will put it here also if there is a need. So this is how it has to be done. You see now, consider if you are making three ABCs, same example, three ABCs. If they are very close to these, say these are diffusion resistors. They are diffusion resistors, and you are putting very close to these. So diffusion means you will be implanting either a boron or a phosphorus or whatever material. Whether if you want to make P plus, this means you are putting boron here. So you see, while if you have studied ion implantation, what will happen is in the B, because areas of diffusion, once they in the drive-in step, so B will get more of boron, while fabrication. Otherwise, in your simulation, it will not show. But while fabricating, what will happen is your B will get more atoms, and so that it will have the resistance value will be less as compared to A and C, though you wanted. So the separation is very important because of diffusion interaction. You can see here, because B is also getting certain from C also, from A also, because this dimension is less. But if you place dummy here and here, then A, B, C will get the same thing, same effect. So then A, B, C are matched resistors. So matching is very, very important. And that is, and then thermoelectric effect. If you see the thermoelectric effect, also known as the Seebeck effect, that is the potential difference that is developed between two dissimilar materials that are at a different temperatures, because you are using a metal and you are using, say, poly resistor. So poly is a silicon. N well, P well, diffusion, they are all these resistor layer which we are making, they are in silicon. and we are using a copper or a aluminium as a metal, right? So there will be a Seebeck effect on when two dissimilar metals are used. So this is a metal thick line, this dark color. So there will be thermoelectric potentials will, if you are placing like this, you can see here this resistor, and if you are placing like this or you are placing like this, in both these things here the thermoelectric potential will add from here to here, but in here it will cancel. So I have 1 2 3 4, 1 2 3 4. These are the resistance segments. They can be poly, they can be N well, they can be P diffusion, N diffusion, poly, or anything. But if I connect like this way, another way of connecting is this also, right? Another way of connecting is this also. But this here thermoelectric potential cancels, here it doesn't cancel. And otherwise also you will see this area will take more because more spacing. It will take more area also. So I will skip some of these now. Capacitors are very, very important, and how to, there are different types of capacitors, poly diffusion, poly metal, but nowadays most of the common capacitors, it is standard and it's very good. It's a metal to metal capacitor. It's known as MIM. Metal insulator metal capacitors are used. And we will discuss about these. PN junction is also a capacitor, as you can see here. It has some limited applications. So it's a MOS gate capacitor. You can see one terminal is gate and source drain. You connect, and source and drain, and you connect together. So this becomes another terminal, and one terminal is gate. So there is a COX and depletion capacitance will come. So the advantage is this capacitance has limited range, but value of capacitance is high. So you can have a poly to poly capacitor. There are two poly lines, red color lines, and there is a feed oxide. They are sitting on feed oxide. These red color are the poly, and in between there is a dielectric. This is bottom plate contact. This is top plate contact. So small bottom plate sitting on a field oxide, it will have some parasitic. You can see this. It is sitting on a Fox. Fox is a field oxide, or it can be isolation, shallow trench isolation. So there will be a capacitance of the bottom plate to the body, to the substrate, which will be more. Top also will have, but the bottom plate will have more parasitic value. And there will be some fringe capacitance here in the side. In the sidewise, there will be some fringe capacitance here. So these are parasitic. Normally it is 10 to 15% of the total capacitor value. Total capacitor value, 10 to 15% is the parasitic which is being added in that. So you have to keep into account those things. So metal insulator metal is the most commonly used capacitor. And as you can see here, so this is the top plate, top metal, and this is the second plate, bottom plate, and there is a dielectric in between. This is the capacitor bottom plate, and but there will be dielectric, and as you can see here, intermediate oxide. So there will be capacitor between parasitic capacitor. This is what this picture is showing for the bottom plate. For the top plate, there will be fringe capacitance which is coming as a parasitic. So this is on a P substrate. So you can see this is the bottom plate. This is the top plate. So I want to have this capacitance C. So I'm taking contact of the bottom plate here, taking contact of the bottom plate, top plate contact I'm taking here. So I want value of C. CB is the parasitic capacitance of the bottom plate to the body. This will be the layout. This will be the layout. So this is the bottom plate. So this is the bottom plate contact. These contacts of square white color you are seeing. So they are of that. And this is the top plate. This one square. This is the top plate contact. This cross you are seeing. This is the top plate contact. Okay, so the capacitance value will be decided by the area of the top plate. This only by the area of this top plate. Bottom plate is bigger in size because you have to take contact at the top. That is why it's more in area, more. But capacitance will be decided by the top plate. And there will be some fringe capacitance here, which is a parasitic and it is modeled. It is 10 to 12%. The foundries will tell you what is the value of these. So these things are modeled edge effects. So randomness will be there. So all these things foundries will tell. So non-uniform undercut fringing effect, they will change the value of the capacitances. The area and perimeter ratio is preserved if we use layout using unit capacitor. So area and perimeter is very, very important here. So this is one case where the area is 1.4 and 1:4. This, if you see the area of this and this block, this is 1:4. And if you see the perimeter, so this is 1:2. Perimeter is 1:2, but there is another case where the area is 1:4 and perimeter is 1:4. And there will not be any undercut in this case. But if you see this case, if there is a undercut of 0.05 undercut is there. Undercut means here we are assuming squarish, very good lines, but when you do a fabrication, it will not be like this. It will not be a clean line. There will be some roughness at these. Those are the undercuts. So roughness will be there. So if you maintain the area and perimeter ratio in two capacitors, if you want matched one, if you maintain the ratio of area and perimeter, this roughness will be divided equally. If you're not maintaining, because roughness will be there on the perimeter only. Perimeter affects the roughness, not the area. So the perimeter, area by perimeter ratio, if they are same, the roughness will be divided. So you can see here, so I wanted like this, but manufacturing will not come like this, right? 90 degree, you cannot do like this. It will be a rounded thing. So this much area is not there. So this is how the etching always causes corner rounding to some extent, because it's a chemical reaction. You cannot have one cannot have a chemical reaction at 90 degrees. Okay, so this means 90-degree corners will be eroded. 270-degree corners will have incomplete removal of material. There will be in here, if I wanted like this, it will come like this. Some material remains here. Here material is not here. Here material removes. I cannot remove this material here. So it is like this. So this is the meaning of corner rounding, undercut. So in order to overcome this effect, use an equal number of 90-degree and 270-degree corners. Right. So if the corners 90-degree and this is the meaning 90-degree and 270. If equal number are there, so here material is cut, here material stays. But if you add these two, then the effect is nullified. So if same thing is there, as you can see here, in this case, it will be, you have made a structure like this, layout like this. This is the actual. On silicon, it will come like this. This one rounded, here rounded, here like this. So there will be some undercut, there will be some external, and there will be some undercut and like. So all these things, and oxide gradient is very important. Variation in dielectric thickness across the various, because capacitance value depend on the dielectric thickness, epsilon A by D, epsilon. So the effect of the oxide thickness in one direction may vary. Okay, so then first of all, if you have to make a if you have to lay out a capacitor, you will choose one unit capacitor, and then say you have to make a 10 nanofarad capacitor. So one way is to make a two plates single capacitor which is 10 nanometer. Another is to make 1 nanometer unit capacitor and make layout 10 of those like this. As shown here, there are 12 of those. There are, sorry, 16 of those. So you make a number of this. So the concept is you make a unit thing, and that unit you replicate and connect in parallel so that you make that value. So in this, the matching becomes more perfect. That is the reason of doing this. So here C1 and C2, because as I told you, in analog design, your absolute value is never used. R1 by R2 is used. And instead of resistance, you have studied the switch capacitor circuits. Resistors take a lot of area, and there are a lot of issues in TCR, VCR is worse, capacitance is better. So, and area is more in case of resistor, particularly high value resistors, it consumes a lot of area. So the better way is to use a capacitor instead of a resistor. So C1 by C2 ratio is used. And so these are the two poly capacitors, C1 and C2. So you will place like this. C1 will be in terms of 2 units. So 2 unit capacitors, you will place one C1 here, one C1 here, 1 unit of C2, 1 unit of C2. So in this, in your x-axis and y-axis, if there are any deviations in the dielectric, they will be nullified, and if you add these two, both these capacitors will be same. Both these capacitors will be same if I lay out like this. So in some of the examples, you see here sensitive to alignment errors in the upper and lower plates, because finally lower bottom plate is made. It's a metal plate. It has a different mask. Say it's a metal 5 and top is metal 6. So there will be some alignment error between these two. It may, one is this and one is the bottom plate is larger because you have to take contact from here. So there is a fringing field is coming. So fringing capacitance will also come. So a structure that minimizes the ratio of perimeter to area. So is that ratio of perimeter to area minimum is a circle. So if you, but it's very difficult to fabricate a circle. So you try to make it as a polygon, as shown like this. So that will have less of these effects, and you will get a better capacitor and better matching also. So for accurate matching of capacitor, you should have a matched parameter ratios. Two capacitors, both the parameters ratios should be matched. Proximity effects in neighboring effects, mismatched long range, mismatched interconnect. Also, all these things will be there in that. So long range, I will skip some of these, and let us come to the transistor. So if this is a transistor, this is drain, this is source, this is gate, you have a contact here, you have a contact on the substrate. So this is how it has to be done. Now, if your W by L is 174, well, W is 174 and L is 1, so it is a wide transistor, and you are making a contact here. In simulation in front end, no issue. It will show you everything good. But once you try to do this fabrication and see, test it on the silicon, you will see a lot of deviations in the specifications which you were requiring. The reason is you see here, I'm making one contact here at the drain, one contact at the source. So the current will flow if it is an NMOS from the drain to the source. So here in a drain, because it's a N plus, so there will be series resistance in the drain. So as you are making a contact here the contact resistance is very less, 2 ohm, 3 ohm or 4 ohm, whatever it is very less. But resistance of the drain or a source is more. Okay, so the current will take the least path. So from drain to source, when the current flows, most of the current will flow here. It will not flow here. Why? Because some resistance is getting added. So most of the current will flow in this area only. Okay, so M1 carries the most current, and so you can assume here this is M1, this is M2, this is M3, this is this. But finally, M1, this is a most of the current is flowing here. Though you have made a wide source, but this area is taking very less current. So what it will turn into a hotspot, and finally it will be a reliability issue. Maybe after 5 months, 6 months, or 5 years or something, this area, because it's taking more current and this area is not taking at all current, so this area will finally be the hotspot and finally may collapse. The life of an IC is supposed to be 20 years, 25 years, so it will not work on that way. So most of the current will be shrunk to this side. So to if you do like this, and these are some numbers, so many ohms per square is the gate resistance, source drain resistance is this, and for n plus and all those things you can. I will share with you these materials. This is a diffusion resistance. So best is you make contacts like this. Don't make one contact. Make contact all throughout. Okay. If you are making contact all throughout and make contact all throughout, so the current will flow through our entire thing like this. And moreover, if the contact resistance of one contact is 5, contact resistance is 5 here, plus source plus this resistance, so it will be 5 here. So but now you are making 3 contacts in parallel, each contact resistance is 5, so 5 ohm, 5 ohm resistance in parallel. So what will be the total contact resistance? It will be less than 2, it will be close to 1.6, 1.7, whereas it was 5 here. So that advantage you are getting here, and current is also uniform from source to drain, which is not the case here. So these are some of the uh, tricks which are used. Another thing, can you make one contact like this, one big contact? As this dark color, black color you are seeing, this shows one contact. Here gate, one contact. You see in a foundry, contact sizes are same. You cannot have different contact sizes. There is a reason for this, and you will, if this is the contact size, the foundry will tell you the contact size because of the etching, and they have seen their model, their etching based on this contact size. So you cannot have different contact size. Only the only thing is what you can do is where the area is more, you make multiple of these contacts. Like this area is more, you can have this size contact, you can have 5 or 10 depending on the area you fill. One reason is if you have put a one contact here and suppose in fabrication it doesn't open, so it will be an open circuit here, your circuit will not work. If you are putting 10 contacts, 5 may open, 5 may not open, but 5 still they are opened. Okay, so then you will have at least a contact. So but here in this case, if you are making one and there it's completely etched out, so you are getting an open circuit. So that is the reason you make number of contacts, use as many contacts as possible. Don't leave the area without contacts. Wherever space is there, you make contacts. So that will help you to reduce the source drain resistance. On the gate also, normally we make contact here, we do not make contact here on the gate. There is a reason for this. Above the channel we don't make contact, we can make the contact of the gate here and here also, two, if it required. Normally it is one, but you can make the contact on the other side of the poly also. So like this, you will have to make this, and you can make the and on the substrate you also make as many contact as possible, so that way you will minimize these various capacitances, you will minimize these resistances. And another thing is how to minimize these various capacitances, that is by fingers. You will make multiple fingers, like instead of one long thing, if I make two fingers, like two fingers, then what is happen is this area, this is a source, it is shared between these two transistors. Okay, so the source capacitance, here the source area is this, here the source area is this half. Source area is half because W is half. Drain remains the same, source is half. So overall, you have reduced your CGS. Okay, so this way, and source to body, you have reduced. If you make it 3, then you can see source to body and drain to body, you have reduced by 2 by 3 times of the original. So these, if you have instead of W by L, you have W by 2 by L and W by 2 by L, two transistor, end result is same. And they are connected in parallel. So 2 fingers, 3 fingers, and beyond this, you can see you won't have much effect, and you will add to more of parasitics. Similarly, poly contact you can have at both sides. You can see here, this is poly, two concepts and multiple drain contacts and source contacts here. So all these things, they help you in circuit performance in analog particularly. So this is an example of a multi-finger layout, shared source drains. So you can see here source drain. This is the gate. This color. So like this, you are able to reduce it. Again, all these things, and then you will add here substrate contact is there because noise. If you don't put a substrate contact, then substrate will be floating. There will be substrate current, there will be interference. You put a substrate contact, and if it's a P substrate, put a zero while using, you connect it to zero, VSS, ground. So the substrate is ground at least, so that it doesn't cause any interference. So you can see here, these are the source substrate contacts. All, so wherever not only one, put as many, where fill the substrate with these contacts, it will be better. It will minimize the noise because it provides a low impedance path. If there is any noise in the substrate, what happens? This is connected to ground, so all noise is going to the ground. Okay, if you are having one contact, it has a contact resistance of 5 ohm. If you have multiple contacts, what will be the contact resistance? It will be maybe 0.1 ohm, 0.2 ohm. So immediately the ground will go to the, immediately any noise will go to the ground. So that is the use of these. And sometimes you have a substrate node here also, surround it by a substrate contact. Maybe it's, see this, you substrate in not all transistor, because you are consuming area also, more area in this. But wherever required, in case of a preamp stage or for a 1 or 2 transistors, wherever required, you can have this. You are eliminating the noise, but you are consuming more area. Okay, so now, so these are another, from the matching point of view. So differential amplifier, there are, as we have studied, there are 2 transistors, M1 and M2. And in a differential amplifier, what is important is the common signal. They only amplify the difference in the signal, V1 minus V2. So the difference is amplified. So this M1 and M2 should be exactly the same. Exactly the same. Now see this transistors here. You can have this way. This is M1, source, drain, and common gate. What is the difference between this? I have this source, I have made common source. So this is source of both these are common here. So I have put a common source. Okay, so this way, this layout will be preferable. And antenna effect means, you see, while fabrication, if there is a metal, and during, because etching is done by plasma, and if there is a large metal, this is the poly, this is source drain, this is the poly, and you have a poly contact, and there is a metal line. So what happens is, first you deposit the metal, aluminum, and then you etch the metal. And while etching the metal, you do a plasma etching. So plasma, you know, there are a lot of ions, electrons, and things like that. So this acts as it's an RF. Under RF, it's a plasma etching is done, and this particular acts as an antenna. So it attracts charge. A lot of charge is attracted on this metal strip, and more charge. So sometimes it can break the dielectric. So that is the antenna effect. So that is to be avoided. So this long, how to avoid so much long metal lines are avoided, which are connected directly to the gate poly. So you make it, break it like this. You break it and take it to the next metal and connect it via via. So only you are using this metal. This segment you have taken to M2 and then use a via to connect. So that way these things are can be minimized, some of these effects. So matching of these components, because this is M1, M2 have to be matched here, M3, M4 have to be matched. So this matching of component is very, very important. The layout is very, very important. You can see here this M1, M2, this transistor is laid out like this. This is the gate. Gate is horizontal. Source, drain. Here, this transistor M2 you have laid out in a different manner so that the gate is vertical. Okay, in a simulation it will not show any effect. It will be, it's okay. But practically once the silicon comes, because process variations will be different. For this gate, there will be some error will be different, and for this transistors, error will be different. So these two transistors will not be the same. So you have to alignment of these gates have to be same, right? You see one of these. Here, what happens is normally implant, when you do the implant, it is done at an angle 7 degree to avoid channeling. So here, and a poly, there's a gate oxide, there's a poly which is a 7,000, 8,000 angstrom thick, and it is at an implant. So what happens is just below here, below the gate at this area towards this area, it won't see any implant. It won't see any implant because of shadowing. Okay, so the here the resistivity sheet resistance of source will be different as compared to the drain. So source and drain are not symmetrical because of this. So though we want source and drain to be symmetrical. Okay, so that effect will be there. So that is the reason. What you do is you don't do this. Gate is not aligned. Gate is horizontal here, vertical here. You do give both the gate horizontal or do both the gate horizontal like this. Then the effect on the source and drain of both the transistors will be same. Here you can see here, if this is the source, here the effect on by shadowing effect on this transistor and on this transistor will be entirely different. Here both the effect will be same because they are aligned. So that is important because of photolithography invariance. So these things make, and current flow you have to see should be in the same direction. When you're matching the current flow, how you can see, because source to drain, current flow is like this, like this. Here the current flow here is like this, here is like this. So current flow should be in the same direction. This means your transistors are aligned in the same direction. Well proximity effect. You see high energy implants to form the well scattering from the edge of the photoresist mask and bending in the silicon surface near well edge, near well edge. So transistor close to the well edge have different properties. So this is the well I have made, but I have put one transistor here, one transistor here. This transistor is close to the edge. This transistor is very far from the edge. Okay, so there will be variations, and this is known as well proximity effect. Why there will be variation? Because of at the edges of the well are formed by high energy implants. So during photoresist, the thickness of the photoresist is normally 20,000, 25,000 angstroms. So near the silicon surface, there will be some scattering and there will be some more ions here. So here the effect will be more, here the effect will be more. And this portion is getting affected, this transistor where the cursor is there. Whereas in this transistor, it is not getting affected. Here it's this particular diffusion is getting affected. So that is the reason. Okay, so distance between gate and STI impacts performance, important for matching. You should not use like this. So if you have to draw two identical structures A and B, and their area as well as their perimeter should be in the same ratio. You see, if you are doing A and B, here the surrounding effects of A and surrounding effect of B are different. Here B is seeing different surrounding. So if I want to make A and B, can be anything. It can be transistor, it can be resistor, it can be capacitor. So here, if I want identical A and B, then I have to make their surroundings identical. How I can make like this? So all these are dummy. I am putting dummy. Now A and B are exactly identical after fabrication. So error, there will be error introduced now also. But the error introduced in A and B, if they are same, then the ratio will remain same. But here the error introduced in B may be more than in the A. So A by B ratio becomes different. So here it's just the components are ratioed all. So here you have to keep the surroundings very put a dummy. Like these are the two transistor M1 M2. Here I put a dummy, here I put a dummy. So dummy is what? If there is a metal line going towards this transistor, you put a dummy metal line here also, so that the surroundings are same. So you have to make surroundings same. Now both the transistors should have same surrounding. You see, if this is a source, you are connecting a source like this. Say this line are going to the source of this, you are connecting a source like this. These are two transistors. You are connecting a source like this. This is nothing wrong in it. It will show exactly. But what happens is the current is flowing here. It goes here. It goes here, and it goes here, and it goes here. But this source, it's saying it will have, because finally this is a metal line. There will be some metal resistance here also. Okay, so the metal resistance from here to here, resistance from here to here will be different. But if I do like this, okay, and apply the voltage here, then current is coming here and then it's getting here and here at the same place. It is from this point to this, and this is seeing the same resistance. From this point to this, and this is seeing the same resistance, which is not the case here. From here to here, here to here, here to here, here to here, resistance is different. So this is not matched, this is matched. Okay, so this is how it is grading. If there is a gradient, I want A and B to be same, but if there is a gradient, this is affected by 5, this is affected by 9. Okay, so this the values will change. Then what is the option? So I will split in two component, two unit A1, A2, B I will split in two. So now say there is a gradient. Here it is 2, here it's 3, here 4, here it's 5. So you see the count the gradient of how much A will be affected. 2 plus 3, 5. A will be affected by 5 and B will be affected by 9 in this layout. But if you do like this A1, B1, B2, A2, then you see A1, 2, A2, 5, it is 7. B1, 3, B2, this also is 7. So A1, B1 will be matched here if you place like this. So this is known as a common centroid layout. Okay, so these is a common centroid. Common centroid. This is cross-coupled common centroid. Here also these components are matched. You have used 2 unit cell. Here you are using 8 unit cells. Okay, so again a common centroid. This you can see here X, variation in X, variation in Y, and see this yellow and blue linear variation. You can see this, both this component will be matched. This is known as a tied, this is known as a cross coupled. Both these things are used. So gradients are compensated in such a manner. In a common centroid layouts for all transistors, metal, capacitors, they are used like this. So any gradients in X and Y, they are compensated. Hello, I think I will stop here and ask for any questions. Hello, any questions from anybody?
Hello.
Yeah, please go ahead.
Sir, what is the maximum width of a transistor that you can lay in standard CMOS process, for example, SCL 180 nanometer?
You see, in an SCL 180 nanometer, as there is a minimum dimension of length, and that is 180, and minimum dimension of width is 220. 220 by 180 is the minimum, and similarly there is a maximum also. And ideally you can have any W, but it is not. I think it is something 2 micron or 2200 micron, 20 2200 nanometer, like that. So the reason I will tell you why it is, you see, if you see the current equation IDS, mu naught Cx W by L VGS minus VT. So the current equation is, the current is dependent on the width, on the length first of all. In a short channel device, if the length is small, if the length is more, if the W is small, W is more, the current it depends on that also. So we have, for each W by L, the model file changes. So that is known as a binned model. In 180 nanometer, it is binned in 9 different categories. There are 9 different models bin wise. So depending on the W by L, there are 9 different bins, right? So they are, and the tool select that bin. You don't have to select that which particular model while using HSpice will go. The tool will select, and if you see the 180 nanometer SCL, you go to the design manual. They have given the all these 9 bins, what will be the length and what will be the W in each of these bins. They have given that information there. And the reason of is, you cannot have, like in a power transistor, it has to take 2 ampere, 3 ampere current. So W will be very high, thousands or
Right,
lakhs maybe.
right.
You cannot have a 1 lakh by 180 nanometer. So you will have fingers, multiple fingers, and that kind of a when aspect ratio is very large, it's not possible to manufacture also. So your layout of a single component has to be squarish in nature, right? One thing should not be very large. Aspect ratio should not be very large. So 1 lakh by 1 unit is cannot be manufactured. Ideally it is okay, but practically it is not. So you will have to split in unit. Any layout, the first thing you do is you make a unit thing, unit transistor. And if a, say, unit size is, say, 2 by 1, that is the unit size. And if your sizes are coming 10 by 1, so this means 2 by 1, you will use 5 those units. It is same like in a building, the brick size is same, right? So
Okay.
you choose the number of bricks depending on your on the wall, how much wide you want. You choose the number of bricks here. It's not that you make different sizes of the brick. So in analog, the best is you decide on a unit size for a resistor, capacitor, inductor, transistor. And in the design, of course, each transistor will have different sizes. So you don't lay out the transistors as per their sizes. There will be a lot of mismatch. So all those transistor components, you lay out as per the unit size. Okay, you use 2 unit, 3 unit, 4 unit, like that.
Thank you, sir.
Hello, sir. Hello.
Yeah, please carry on.
Sir, how to find out the process parameters as the tech node varies, like mu and COX and all?
That No, process parameters are how much the VT, those process parameters are mapped directly to the threshold voltage. Right, so each foundry will give you the variation in how much, like in 180, if the VT is 400 millivolt, they will tell you within the wafer, there can be variation of say 10 millivolt or 20 millivolt in the threshold voltage. Okay, so that there may be variation in the dielectric, gate oxide, there may be variation in the channel implants. So all that effect is translated to the variation in the threshold voltage. So the designer they use when you is the concept of your slow, fast transistor. So what you do, you vary the VT only. So all those effects, because finally what is important? Any process parameter variation, it will result in variation in the threshold voltage. So you assume, and each foundry will give you that my in a chip in a neighborhood close, you are placing transistor very close to each other. The variation can be 2 millivolt or 3 millivolt. If you are placing transistor very far, like in a 8-inch diameter, 8-inch dia wafer, from one end to the other end, the variation can be 10 millivolt or 20 millivolt. But if you are placing transistor very close to each other, the variation can be 1 millivolt itself. So that is how it is, and the chip sizes are 5 by 5 micron, 5 by 5 mm, or 10 by 10 mm. So within 5 by 5 mm, the variation won't be much. But across the wafer, there can be 10 millivolt, 20 millivolt variations. And also the foundries will tell you the value of these with respect to temperature. Low temperature, high temperature, how much delta is there. So all those, if you see the design manual, it's a 100-page, 120-page manual. All these variations with respect to temperature, with global variations, local variations, they call it. So all those values are given.
Thank you, sir. So one more thing, like with respect to 180 nanometer, we just keep the supply voltage around 1.8 volts. So similarly, like that, like 45 nanometer, what's the maximum voltage we can keep it, the supply voltage?
45, it is 0.8 volt. It's from
0.8.
logic, yeah, 0.8 volt. Even at 90 nanometer, you have 1 volt and 0.8 volt.
Okay,
And
sir.
but for the IO pads, maybe at 1.8 volt,
Okay,
right?
sir.
Because but the logic will be at low voltage, 0.8 volts.
Okay. The threshold voltage, sir, like,
Threshold voltage 300, 350. You cannot reduce below 300 millivolt.
okay.
300, 350, that's all. Below 300, you cannot, because ion by, because set threshold slope, ST, okay, ideally is 60 millivolt per decade, but normally it is 80 millivolt per decade. So 80 millivolt per decade means uh, if it is a 300 millivolt, so in 4 decades, like 10 raised to the power 4 times your off current will reduce. 10,000 times will reduce from on to off. So normally for a transistor, you need ion by I of to be infinity, or it has to be 10 raised to the power 6, 7 or 8. Okay, so you cannot reduce VTs to a lower than 300 or 350 millivolt, and for a 1.8 volt, it is 400 millivolt. For 1.8 volt, it is 500 millivolt, like that. So it is 300 to 500 millivolt in this range for VDDs of 1 volt to even 5 volt. The VDD is in that range. For a 10 volt device, it used to be close to 1 volt.
Okay, sir. Thank you, sir. Thank you.
So, okay, then thank you. If there are no other questions, thank you very much.